It's a great pleasure to welcome everyone to the second lecture, Nirenberg lecture this year. Yevgeny Liokumovich from University of Toronto will speak about minimal surfaces and quantitative topology. So the lecture will be recorded, and I would like everyone to mute yourself unless you would like to ask a question. Thank you. Zhenya, it's all yours.
Thank you very much for the introduction, and thank you very much to the organizers for this opportunity to deliver these lectures. During my talk, please feel free to ask a question or type a question into chat. I will be keeping an eye and I will try to answer all the questions to the best of my ability. So today I'm going to talk about minimal surfaces and quantitative topology, and more specifically about applications of the quantitative topology of the space of cycles to some results about minimal surfaces. And our starting point will be a certain point of view that Gromov introduced in the 1980s, a more theoretic point of view on eigenvalues of the Laplacian. We will look at a compact Riemannian manifold and the Hilbert space of functions on this manifold. And we'll consider an energy function from this Hilbert space into R. And if this energy function is invariant under multiplication by a non-zero scalar, then we can pass this function to the space of lines in our Hilbert space. We can consider the quotient under multiplication by a non-zero scalar. And now our function will then induce a function on this space of lines in the Hilbert space. And then, because this space has non-trivial homology and cohomology in all dimensions, so if we consider with mod 2 coefficients, then the cohomologies will be equal to Z2 for all k, we can now start considering non-trivial families of functions in the space P. And we can do Morse theory. We can consider the maximum, we can minimize the maximum of these families in a fixed cohomology class. So if you pick a generator of the cohomology, and we will consider all the non-trivial maps, say from RPK, corresponding to this generator, then we can define this min-max quantity, the smallest maximum of the energy among all families in this cohomology class. And so what we've just done is that we found a kind of somewhat unusually looking way of formulating Rayleigh quotients for the eigenvalues of the Laplacian. If we pick our Hilbert space to be the Sobolev functions on our manifold, and we pick our energy as a Rayleigh quotient, then these min-max quantities will be precisely the eigenvalues of the Laplacian. But we can also consider other energies, other homogeneous energies. For example, we can look at the Rayleigh quotient for the P Laplacian. So let me make a note here that in this case, our space is not really a Hilbert space, it's just a Banach space. However, we can still construct this quotient, and this space called, it will be a Z2 space, and it will have a cohomology ring the same as the cohomology ring of the infinite projective space. So this definition will still make sense. And the kind of functional that we will be interested in today is volumes of hypersurfaces in our manifold. So if we can look at the energy equal just to the n-1 dimensional volume of the zero set of a function. And notice that this functional will also be invariant under the multiplication by a constant. So the above definition makes sense, and we will have the corresponding sequence of these min-max quantities. And you can think of them as a kind of nonlinear analog of the eigenvalues of the Laplacian. So I haven't specified what our space is yet. We will do that a little bit later. So Gromov's insight and his point of view that if we consider these min-max problems in this context, then the fact that we know so much about the eigenvalues of the Laplacian may guide us in trying to understand other more complicated min-max problems like volumes of minimal hypersurfaces, or for volumes of hypersurfaces in our space. And the key common feature that exists here is the topological structure of the underlying space of Rp infinity. So his insight is that we can use the cohomology ring of P to prove things about these min-max quantities. And let me illustrate this by proving one particular lemma, which will then play a role in some of the subsequent developments. So I will try to prove it in this generality. If we know something about how our function, the energy of our function is related to the energy of a restriction of our function on some subset, then we can use that to prove interesting results. So in our case, we are keeping in mind this functional, the volume of the zero set. And if you have some hypersurface, then of course the volume of the whole hypersurface, so this is our hypersurface, the nodal set, the zero set of our function. So of course the volume of this hypersurface will be greater than the volume of the restriction to some two subsets, U1 and U2. So if we have this additional property for our energy, then together with the cohomology structure of P, we can use that to prove a relationship between the second min-max quantity for the union of these two sets and the sum of their first min-max quantities. So let me go through the proof. We will use a fact from topology that if you have two elements in the cohomology of the space, and each one of them vanishes on some subset of your space V1, and the other one vanishes on the subset of the space V2, then their cup product will vanish on the union of these two spaces. So this is a fact that follows from the, say, Maya-Vittori's long exact sequence. And it is a fact that has a long history. It goes back, for example, to Lusternik and Schnirelmann's proof of existence of three simple closed geodesics on the three sphere. So it has a long history of applications in geometric analysis. And so we will now proceed from this fact as follows. We will define a subset of our P as the set of all functions so that the restriction of the energies to Ui have less than W1 of Ui. And we will observe that the generator of our cohomology vanishes on these sets. Well, why is that? Well, if this is our M and this is our Ui, then there is a natural map from P of M into P of Ui, just the restriction map. And then this map descends to the map on cohomologies. And so the cohomology rings will actually be isomorphic. So if you have a non-trivial sort of family in M, then that family also has to be, the restriction of that family to Ui should also be non-trivial in the first cohomology. And so now, if we consider a family of functions that have their energy less than WU1 plus W1U1 plus W1U2, then we know that either in one set U1 or in the other set U1, it has to have energy less than W1 or W1U1 or W1U2. So in particular, this family lies in the union of V1 and V2. And since it lies in the union of V1 and V2, we know that the cup product of alpha 1 and alpha 1 will vanish by our fact from topology. And that's precisely our alpha 2, the generator of the second cohomology. So it follows that if you have a non-trivial family from the point of view of the second cohomology in the union of U1 and U2, then it has to have an element, a function, where the energies have to be greater or equal than W1 U1 plus W1 U2. So this is how the topology of our underlying space helps us to prove inequalities about these min-max quantities. Okay, so let us now try to define exactly what kind of space we want to work with if you want to study hypersurfaces in the manifold. And we are interested, our end goal is to understand minimal hypersurfaces in our manifold. So we would like to have nice compactness properties, and we would like to be able to prove regularity for the minimal hypersurface we construct. And so the space that has this nice property is the space of flat cycles. So let me quickly describe what this is. So if you have two Lipschitz cycles with mod 2 coefficients, just Lipschitz maps from a simplicial complex or polyhedral complex with mod 2 coefficients or with integer coefficients, but today we work with mod 2 coefficients, then you can define a norm or a distance function on this space. So if this is your Z1, this is your Z2, then you consider the infimum of all chains tau, so that the boundary of tau is the difference between Z1 and Z2. So Z1 actually can have long and Z2 nasty necks, or even handles that are very small. But if they bound small amount of volume, then these two cycles will be close to each other. And now we can define this space of n-1 dimensional flat cycles to be the completion of the quotient of all Lipschitz k-cycles by this equivalence relation, right? So if you have a cycle and another cycle, and in between they bound something of 0 and k plus 1 dimensional, in this case n-dimensional volume, then we disregard the difference. From a kind of geometric point of view, they're all the same. And the reparametrization of geometrically the same cycle is also all the same to us. So this definition kind of nice in capturing the geometric picture of what the hypersurface looks like. And so it's a result of many people, but finally by Federer, but also building on the works of Federer, Fleming, and Georgi, and Simons, and others, that if you are in this space and you consider some homology class, then you can consider a sequence going to the infimum of the volume in that homology class. So smaller and smaller, and then a subsequence of that will in fact converge to a minimal hypersurface in that homology class, and the volume of that minimal hypersurface will be the infimum of the volumes of cycles in the homology class. And this minimal hypersurface will be nice. It will be embedded, smooth, minimal hypersurface in these dimensions. In larger dimensions, you may have a small singular set. So this is a nice space from the point of view of finding minimal hypersurfaces. But now, instead of just minimizing, we want to do Morse theory on that space. We want to consider min-max quantities, like the ones that we just described. So let us talk about a little bit about the topology of this space. And it follows from the work of Almgren that this space of hypersurfaces is weakly homotopy equivalent to RP infinity. And in this case, we can see that. So if this is our Hilbert space of some nice functions, so that their zero sets are nice Lipschitz hypersurfaces, and we have this map that we defined previously into RP infinity, then we can map this into the space of n-dimensional mod 2 cycles, simply by taking our function f and sending it to the set f of x greater or equal than 0. And then we have here a 2-to-1 map into the space of Zn minus 1 cycles, because if you have, say, some manifold Sn, and then you have a cycle, then there are precisely two ways of filling that cycle. You can either fill on one side or on the other side. So the boundary map is precisely a 2-to-1 map from the space of n-dimensional chains into the space of n-1 cycles. And so this diagram will commute, and it will induce a weak homotopy equivalence. It will induce an isomorphisms on the homotopy groups, and in particular, it will induce isomorphism on the cohomology groups. So this space will have the same cohomology ring as RP infinity. And we can think of it as a kind of enlargement of some nice space of zero sets of some nice functions. So now with this topology, we can do Morse theory. We can try to do Morse theory, and we can consider different cohomology classes, and to each cohomology class we will have families of non-trivial cycles, flat cycles. So we will define a K-sweep out to be the family which corresponds to the kth power of the generator of the cohomology. So in the previous examples, we thought of this as RPK, but it could be some other manifold. The point is that it induces non-trivial map on the kth cohomology of Zn-1. And so we can define these mean-wax quantities, which I will call K-wastes, to be consistent with my previous talk, where one waste was an optimal way to sweep out my manifold by hypersurfaces once. And now here, this is a higher parameter version of what I talked about last time. So these are now K-parameter families of cycles. And as usual, the hope is that if you have this as your space of cycles and you have some non-trivial family, then by minimizing the maximum, by pushing the maximum as low as possible, you will be able to find the critical point of your functional, in this case, volume functional. And so by minimizing in this non-trivial family, so this is my non-trivial family, f of x, phi of x, and so I'm trying to make the maximum as small as possible, and that's why I want to obtain a critical point, and my hope that this critical point will be precisely the minimal hypersurface. And this indeed turns out to be true. It's a result of the work of many people. It was started by Almgren in the 60s, then considerably advanced by Pitts, Shane, and Simon in the 80s. And more recently, a lot of the development has been happening because of Fernando Marques and Andre Neves. And very recently, Shinju proved multiplicity 1 conjecture in this setting. And so we have that in dimensions between 3 and 7. The K waste is equal to sum of volumes of minimal hypersurfaces, which are all disjoint, embedded, smooth, And these ni's in general are integers, but for a generic metric, it's possible to make the min-max argument in such a way that these ni's are all equal to 1. We have in multiplicity 1 minimal hypersurfaces, and the sum of Morse indices is equal to the number of parameters. So this corresponds to the intuitive picture that the Morse index of the saddle point will be exactly equal to the dimension of the space. The number of ways to go down from here is exactly the dimension of our non-trivial family. Should there be another function like E? You mean instead of, so there's a question, should there be another function? You mean instead of volume? So it's in the definition of, yes, yeah. So, yeah, thank you very much. Like volume, right. It's a typo. So we are looking at the, thank you very much. So we are looking exactly at the volume of phi of x. Yeah, sorry about that. So we are looking at the volume of the corresponding hypersurface. That's our functional. Right, and the same here. Okay, so so these are k-wastes, which are sometimes called nonlinear spectrum by analogy with eigenvalues, which correspond to Eigenvalues of the Laplacian, which is a kind of linear spectrum, correspond to a linear operator. And let me list some of the things that we know about them from the quantitative point of view. When can we actually calculate them and when can we estimate them? And I will compare it in contrast to actual eigenvalues of the Laplacian. So in the case of the standard metric on the n-sphere, well, we very well know what the eigenvalues of the Laplacian are. The eigenfunctions are spherical harmonics, and the eigenvalues we know. But in this case, we know only the first several k-wastes. So if you have a sphere, then you can consider the space of hypersurfaces given by intersecting your sphere with some hyperplane. And that gives you an n+1 dimensional space. And so you will have n+1 wastes just equal to the volume of the equator. But beyond that, we don't really know much. For example, the fifth waste was calculated by Fernando Marques and Andre Neves, and they show that it's equal to that it corresponds to the minimal Clifford torus, and that was a key step in their proof of the Wilmore conjecture. And it is quite highly non-trivial, and so the larger ones we don't know. Let me mention that there is a work of Nicolaou Aix, who calculated the wastes up to 8, I believe, wastes from 1 to 8 of the round 2 sphere. But again, more than that, we don't know. If we now relax what we ask and just try to see some bounds for the wastes, then there's a result of Gromov and the later different proof by Guth that allows us to estimate the k-wastes of an n-sphere in terms of its volume. Right, and we have some constants 1 and 2 here, and you can see that the growth is like k to the power 1 over n. And now let me describe some other results, and I will compare them to what we know about the eigenvalues of the Laplacian. If we look at the Riemannian surfaces of genus gamma, then in the spectral geometry. It's a classical subject, beginning with the works of Hirsch for the round sphere, and Hirsch for the sphere, and then Yang Yao for the first eigenvalue of surfaces, and Corrivar for high eigenvalues of surfaces. And of course, I'm not mentioning many other people who have contributed to the subject. They estimated the kth eigenvalue of Laplacian in terms of genus and k. And several years ago, I proved a similar bound for the k wastes on surfaces in terms of k and genus and the area of the surface. If in addition we assume non-negative Ricci, then there is a result of Li and Yao, and there is also a result of Buser that bound the kth eigenvalue in terms of k. And we have a similar result for wastes. Finally, for minimizing the eigenvalues in the conformal class, there is a result of Asma Hassanejad, which generalizes results of Corrivar and Li Yao to give an estimate in terms of this conformal invariant minimal conformal volume, which is defined as the smallest volume of the metric in the same conformal class, which has Ricci curvature bounded by -1. One can calculate that for surfaces, it's proportional to the genus. By Gauss-Bonnet, it's equal to genus times a constant. And we have a similar bound for the first waste of manifold in terms of this minimal conformal volume. And I believe the result is true for all k, but it's an open problem. What's interesting here is that even though the definitions of wastes is different from the definitions of eigenvalues, the ideas and proofs in the case of eigenvalues rely on clever decomposition of the manifold into pieces with nice control on their volume and the size of their boundary. And very similar thing is needed to prove bounds on wastes. So the proofs of this thing all rely on some ideas from the proofs of the eigenvalue estimates. For example, the length area method, where you use that the gradient of f squared dv is a conformal invariant, or a coarea inequality, or in the case of surfaces, the thin-thick decomposition, which gives you a nice idea of how a surface in the conformal class looks like. And I suspect that some similar ideas could lead to the proof of this more general inequality. Okay, well, a famous classical result about eigenvalues of the Laplacian is the Weyl law, which asserts that for every Riemannian manifold, the asymptotic behavior of eigenvalues is all the same and only depends on the manifold on the volume of the manifold, not the particular geometry or curvature of the manifold. And Gromov conjectured that a similar asymptotic behavior should hold for other nonlinear analogs of the eigenvalues, and in particular for the k wastes. So this was something that we proved with Fernando Marques and Andre Neves, that for any Riemannian manifold, the ratio of k wastes to k to the power 1 over n is equal to some constant times the volume to the appropriate power. Notice that this constant is straightforward to figure out because we know what it is for simple objects like cubes or spheres. But here we don't know wastes of any simple object. So it is an open problem what this constant is, even in dimension 2. And Weyl law has recently been used in study of minimal hypersurfaces Marques and Neves used it to prove density of minimal hypersurfaces for generic metrics, that for a generic metric, every small set intersects some closed smooth minimal hypersurface. And Antoine Sonquist, Fernando Marques and André Neves proved a stronger property, equidistribution of minimal hypersurfaces for generic metrics. And some similar but somewhat different asymptotic bounds, asymptotic Y laws were proven by Song for complete non-compact manifolds, and he used that in his proof of Yau's conjecture. And recently, Ilya Mazurovsky used a similar strategy to our proof of the Y law to prove the Y law for P Laplacian, which was conjectured by Leonid Friedlander. So let me now talk a little bit about the proof of the Y law. We'll start with the cube, and we will use the argument that I described in the very beginning, which allows us to relate k-wastes of small subsets to the k-waste of the whole thing. We will start by considering this omega k tilde, the ratio of omega k to the power 1 over n. From the Gromov-Guth bound, we know that these are bounded by constant from below, from above, as k goes to infinity. So they're bounded away from 0 and from infinity. We would like to prove that the lim_inf is equal to the lim_sup. And so we pick q much, much larger than p, much, much larger than 0, so that this q waste is close to the lim_inf and the p waste is close to the lim_sup. And now we will consider our cube, and we will subdivide into n smaller cubes, and we can pack them quite efficiently. So we will pick n cubes where we will want n to be on the order of q over p. Then the length of the side of the cube will be something like 1 over n to the power 1 over n, which is something like p over q to the power 1 over n. And now we would like to relate the p waste of these small cubes, qi, to the q waste of the whole thing, using the inequality that I described in the beginning, using the cohomology structure of the space of cycles. More precisely, we have the following inequalities. So our definition of the q tilde, of the tilde q width, is just q width divided by q to the 1 over n. Then this is greater or equal than the sum, this is the number of our cubes, of all the p wastes of this little cubes qi. But these little cubes qi are nothing else but the usual cube, which is scaled, right? And so we can scale them back, and then we have that the p waste of qi is equal to the r to the power of n minus 1 times the p waste of the unit cube. So we are thinking about volumes of hypersurfaces, so they scale like r to the power n minus 1. And now if we translate that into, if you plug in p and q, then this is going to be just p over q to the power of n minus 1 over n times the p width 0, 1. This is now what we have here. And then when we bring p's and q's together, so we have on the order of n, on the order of n, that is q over p such cubes. And so we will have some cancellation happen, and we will obtain p to the power minus 1 over n times the p wastes of the cube, which is precisely the omega p. In other words, on one side we had lim inf, and on the other side we had lim sup. And because lim inf is greater or equal than lim sup, we must have equality between the two. So this is how we prove the Weyl law for cubes. Any questions so far? The next step is to consider the open sets. So if you have a connected open set in Rn, then you can play a similar game by packing small copies of this set in an efficient way, and then similar type of arguments will work and will give you a Weyl law for these sets. Finally, we want to consider Riemannian manifolds. And then in this case, we can't quite do the same thing. To get a lower bound, we can use packings of cubes or open sets inside, but to get the bound from above, we need to do something else because we can't pack copies of Riemannian manifolds inside them. But what we observe is that we can now cut our manifold into small pieces. We can consider a decomposition of manifold or a kind of a tessellation into small pieces. And each of those small pieces can be mapped with 1 plus epsilon Lipschitz bijective homeomorphism into Rn. So we can map them all into Rn. And then we can in fact think about them as just one connected set. If necessary, we can connect them all by small tubes of very small volume. And so we now have this large set in Rn. And for this large set, for sufficiently big K, we can define an almost optimal K parameter family sweeping out this set. We can then put back our sweep out into our manifold. But now these are no longer going to be nice relative cycles. These are just going to be some chains which do not really constitute a K sweep out. However, we notice that in order to construct a nice K sweep out, we need to use up pieces of our tessellation. And if our K is much, much greater than the size of this subdivision, then we don't care if we have to use the whole all boundaries of all of these sets. Because we are working with mod 2 cycles, each phase here will only be used at most once. And so if K is large, the total volume of all of these tessellations and of all of the connecting, let me use this color, of all of the connecting chains here will be small compared to K. So how do we exactly glue these things together? Well, an instructive situation to look at is if you have two regions, like two cubes close to each other, having a common face, and you have a k-sweep out, relative k-sweep out of one of the cubes, and you have a relative k-sweep out of the other cube. And so what you want to do is you want to now connect those pieces of their boundaries that go into this common interface. So you want to introduce a continuous family of chains whose boundary are the boundaries of the cycles in here and in there, in the two sides. And then this new family will be your nice sweep out of the union of the two cubes. And you can see that you really have just two choices. Either you feel here or you feel outside. So in this case, either you feel one or the other. And a little bit of topology tells you that you really have a way to make a consistent choice for the whole family. Now, these two families in one side and the other side can be very large, and the size of the boundary can be very large. But when you're filling them in, your cycles are n-1 dimensional cycles contained in an n-1 dimensional interface. So the most volume you can pick up from that is the volume of this interface, of that face. So you don't have to worry about having too much volume here. This is how our proof proceeds for Riemannian manifolds. So let me discuss a little bit the situation in higher codimension. If we revisit the topology of the space of cycles and the definition, then everything proceeds in about the same way. We can define m-dimensional flat cycles the same way we defined codimension 1 cycles, how we define hypersurfaces. And then the cohomology ring of that space will be larger, it will be richer, but all of the families that correspond to the cut powers of the generator of the cohomology will all be there. We will have some additional ones, but all of these non-trivial families that correspond to taking cut powers of the sweep out. So if you have a codimension 1 space, sorry, if you have a codimension 2 family, you can consider slicing your cube by one-dimensional cycles. Then it will be a 2-parameter family of 1 cycles, and it will correspond to non-trivial cohomologous class in the space of 1 cycles. And then you can start taking cup powers, and they all will be corresponding to some non-trivial families. So we can define k-sweep outs by taking these cup powers. And then again, so this is going to be k-dimensional volume of phi of x. We can define the corresponding, m-dimensional volume of phi of x. And so we can define corresponding k-parameter families of these n cycles. So in this case, we believe that the Weyl law still holds. And in fact, in our work with Fernando and Andre, we already proved it for open subsets of Euclidean space because the scaling argument proceeds the same way. However, the manifold argument doesn't work. And so let me make some comments about work in progress with Larry Guth, where we prove this result for codimension 2 cycles. We hope that the methods can be pushed further to prove it in all codimensions, but we cannot do that at the moment yet. And let me comment on what seems to be the difficulty in this case. So if we go back to the proof, then one of the key steps in the manifold case was to consider two regions, or say two cubes, C1 and C2. And then we have a k-parameter family sweeping out the first cube and the second cube. And then we would like to construct a k-parameter family that sweeps out the union of the two cubes. Before, if you have two cycles like that, then even if the size of the boundary is very large, you can connect these two cycles together with mass that doesn't exceed the mass of this face. But in this situation, you can no longer do that. So your bound on the mass of the cycles doesn't tell you anything about the size of the boundary of the cycles. And so the boundary can be very, very large. And now you want to connect all of these high codimension cycles together to get a new nice family of cycles in the union. Even if you somehow could get a nice bound on the size of these cycles, you now have this. So in this example, we're looking at the family of one-dimensional cycles in this three-dimensional cubes. Then in this interface, we will see a family of zero-dimensional cycles, and we would like to somehow find the feeling of these zero-dimensional cycles. And we would like it to be not just feeling of one cycle, but a feeling of a family of cycles. We would like it to be a continuous family of feelings. Oops. So the two things that we would like to do is to have a kind of parametric version of coherent inequality, where we can use the bound on the mass of these cycles to wiggle this interface and to get the bound on the intersection of that interface, this boundary. And after that, we would like to have a parametric, isoparametric inequality. If you have a family of cycles and you have a bound on their size, then you can construct a family of feelings with a bound on their size. So let me state this second statement in the form of a conjecture. So we have a proof of that in the case of m equal to n minus 2, in the case of codimension 2 cycles. But it's an interesting question to try to prove that in all codimensions. And I believe this then implies, together with the parametric coherent inequality, would imply the Weyl law in all codimensions, where you're looking at a family of cycles and you look at a contractible family of cycles. And so for topological reasons, you have a family of feelings. But you would like to also have a bound on the sizes of the family of feelings. And then you have this somewhat strange power in front after for volume. So the reason you have that power that's kind of different from what you usually see in isoparametric inequalities is because you're interested in the specific situation where you have a small amount of space and a lot of mass is crammed into that space. And then the best exponent that you have is this one, not the one that you usually see in the isoparametric inequality. And the working with families of cycles is somewhat technical, so you would like to be able to wiggle them around a little bit. So the statement is not about the exact family, but a kind of a small perturbation of that family. And we also allow some extra mass over here in case you may need it. And this also suggests a different isoperimetric inequality, which is not directly related to the Weyl law, but I think is interesting on its own right, if we consider families of m-dimensional cycles in Rn, in the Euclidean space. Or then it is natural to ask whether one can prove a parametric isoperimetric inequality for this family of cycles, now with the usual exponent that you usually see in high codimension isoperimetric inequality. So we know that if you have some m-dimensional cycle in Rn, then it is possible to find a filling of that cycle whose mass is at most, so that's a mistake. What I mean is m plus 1 over m. So m is the dimensional of the cycle. So this is cycle z, m-dimensional. This is m plus 1 dimensional filling of the cycle. And so we would like to bound the volume, the m plus 1 volume of tau by constant times m volume of z to the appropriate power. But what if instead of one cycle, you have a one parameter family of cycles? Even for one-dimensional cycles, it's already non-trivial, right? Because, you know, for one-dimensional cycle, the best thing you can do is you can just take a cone from a point on the boundary. But now for a one parameter family of cycles, these may separate and move far from each other, and you need to do something with your cones. You need to jump from one cone to a different cone in a continuous way. So even for one-dimensional cycles in R3, there is something to do here. And I think it's an interesting problem in general dimensions as well. So in the last couple of minutes, let me mention some other interesting problems and directions. One of them is that, notice that I talked about the space of cycles always with mod 2 coefficients, but it's interesting to ask what's going on with what's happening with other coefficients. If we look at the space of m-dimensional cycles with coefficients in the integers, then when m is equal to n minus 1, the space is not very interesting. It's weakly homotopy equivalent to just a circle. But when we look at n equal to minus 2, and if our manifold is simply connected, say m is Sn, then this space is actually quite interesting. It's going to be Cp infinity. And so it is interesting to ask what kind of quantitative bounds we can obtain in this case. We can now define the k wastes corresponding to integer coefficients. And in this case, even crude bounds are not known. The simplest case would be to look at the space of one-dimensional cycles in S3 with z coefficients. Then it is not clear how fast omega k grows. So it is conjectured that it grows like k to the power 2/3, but it's not known. So the lower bound actually is known. It follows from the kappa argument that I talked about before. But the best upper bound known right now is the linear upper bound. So that's an interesting question. Okay, and I think I'm somewhat out of time, so I will allow some time for questions. Thank you.
Thank you very much for a great talk. Are there any questions?
So there's a question. Can this method be used to prove under certain condition the Weyl law for length of closed geodesics, say on a 3 manifold? Okay, that's an excellent question. So the interesting thing about this min-max construction is that it gives nice regularity in dimensions between 3 and 7. But for one-dimensional objects, for curves, the min-max argument does not produce closed geodesics, but instead produces geodesic networks. So a geodesic network is a graph which is a critical point of the length functional. So for example, so let me draw an example on S3, so on S2. So on S2, that would be something like this. 3 half equators meeting together and making 120-degree angles. And so, right, so the Weyl law can be used to prove, so we can use this to prove results about length of these stationary geodesic networks, which may not be closed geodesics. And we can use the Weyl law in high codimension to prove things, hopefully to prove things like maybe equidistribution and density of such objects in high dimensions.
Great, thank you.
I have a question. So for the one cycles in S3, will like Hopf bundle realize anything?
Right. Well, yeah. I mean, it realizes.
Is it a good sweep out?
Yes, it is. Yes, it is a good sweep out, I believe. Right.
Because this is also related to eigenvalue of Laplacians on one forms.
Right.
And I'm wondering if for other manifolds you can have other. So the ground state of
right.
Laplacian on one forms on the 3-sphere is exactly that. So
right. Right.
I wonder if on other manifolds you can have some relation between sweep outs and eigenvalues for differential forms. But so maybe this is something which, if there are other examples, it could be somewhat interesting, or where you could really have some bounds relating these things.
So the kind of ground state, the smallest value of waste on the round sphere, is known. It follows from the works of Almgren and Gromov that I mentioned last time. But when we look at the higher parameter ones, this is when it becomes unknown.
I see. And so another question, I don't know if it maybe it's kind of too naive. So in the Weyl's proof of Weyl law for, I don't know, domains, it was very useful to look at the different boundary conditions for manifolds with boundary, and then to prove some kind of monotonicity results, that if you change the boundary conditions, the eigenvalues increase or decrease, that kind of stuff. So do you think that something like this could be useful, or maybe something like this is known for sweep outs? But again, I don't know.
Yeah, that's a very good question. What role boundary plays? Or,
yes, because so if you are sweeping and then you insist on something happening on the boundary, but I'm not sure if, at least for eigenfunctions, that seems to be interesting and useful. Right.
Yeah, that's a good question. So the results that I stated, they hold for closed manifolds with cycles and for manifolds with boundary for relative cycles. And we don't make any requirements on what exactly is happening with the boundaries. They may become very, very large. We don't control the supremum of the sizes of the boundaries of the cycles. And we don't require that we start from the boundary somehow. go in. So it's an interesting question about, because if, for example, one tries to study the higher order Weyl law, a high order approximation for the asymptotic expansion, then the boundary will play a role there. And maybe one has to consider different kinds of families.
So for eigenfunctions, there are some very elementary things like Dirichlet boundary condition, Neumann boundary condition.
Right, right. Yeah, it's unclear what I guess these weights are more naturally correspond to Neumann boundary conditions for eigenvalues, the one that we consider, than Dirichlet, I would suppose. And I guess one could say that Dirichlet are the ones that start from the boundary, but it's hard to kind of make sense of that.
Yeah,
what it exactly means.
Can I ask another question?
Sure. Yes.
So it's about the very beginning where you had the additivity property for your wastes. So this property is satisfied by the volume functional, right? But for the eigenvalue, you will have something with maximum, I presume, right? Instead
exactly.
Of
yes.
Max.
Maximum, yes.
So is there some sort of natural functional of intermediate behavior where you get like W1 to the P, W1 to the P, and everything is taken to the power 1 over P?
Yeah, very nice question.
Yeah, one of them is like L infinity, another one is like
right, yes.
L1.
Yes. I think for the P Laplacian, you also get something like the maximum.
Yeah, you should get a max. Yeah. So it's
so
more
it's
a question
not,
of like.
So the P Laplacian doesn't give you intermediate. Yeah, I'm not sure. That's a good question.
Thank you.
So Sachin is asking, is the sweep out in your sense related to the Rayleigh min-max property of eigenvalues?
That's right. That's right. It's related in that, well, it's kind of analogous. So for the Rayleigh, we can think about the Rayleigh min-max property of the eigenvalues as the from the more theoretic topological point of view, and then we are looking at this min-max quantities, critical points of this functional. And then we change perspective and we forget about the fact that these are actually nice linear projective planes in the case of the eigenvalues. And the more general nonlinear case, these are just some non-trivial maps. And we think about them as non-trivial maps and as critical points of other functional, like the volume functional. And in both cases, somehow, what was maybe not so apparent in the case of eigenvalues is that the cohomology structure of RP infinity is something that gives us more information about these and allows us to prove things by relating them. By relating different nonlinear eigenvalues to each other.
Are there any other questions?
Hi, sorry, I have one more questions. Also, okay, so for the Weyl law, I wonder whether it's more intrinsic characterization of what kind of spectrum would you expect a Weyl law? Like the volume spectrum and eigenvalue spectrum, they come from first like min-max construction, and then they have certain discrete property, which like the dimension of each index is finite. And the proof for the Weyl of the volume spectrum and the eigenvalue spectrum, they share some similarity. And I wonder whether you know that there's maybe some intrinsic properties that will guarantee which would produce a Weyl law of this type, or like the nonlinear analog that Gromov was interested, whether they all share those min-max property and some discreteness in the spectrum. Okay, that's my question.
Yeah, thank you. Yeah, great question. Right. Yes, I'm not sure about that. So right now it's all still at the level of an analogy. And if you look at the recent proof of the Weyl law for the P Laplacian, it also doesn't go, I mean, it is similar to our proof, but it uses other things. So for example, here there's a different property, there's this maximum property. And so some of the arguments have to be somewhat different. So besides the fact that both things heavily rely on the fact that we are dealing with RP infinity and we have this nice cohomology structure, yeah, it's not clear what is the most general setup here, right? So I'm not sure what's the right way to generalize it in a way that you could have a statement that would hold for a very large class of eigenvalues, and you just have one proof that works for all of them. And okay. the various bounds on that I mentioned on quantitative bounds that I mentioned at some point. There was this table. Yeah, right here. So over here also, the proofs are somewhat similar, but they're different. So it's kind of hard to formalize what exactly is the analogy. It's just that things that are useful for one tend to be useful for the other, but not exactly in the same way and not always.
Okay, thank you.
Well, okay. If there are no further questions, let's thank Zhenya once again.